Hello guys, hope you're doing well. Yesterday and welcome to this chapter, as I promised, talk about the combination of different systems. Because in this chapter we saw kind of criterias and fundamental part like system itself, but right now the time that we have combined them together. If you know, most of the time we do have the parallel and some kind of series system together, but let's combine it with some kind of feedback method. So it is really fun. Without further ado, let's talk. So as I just mentioned before, right now the reason that we are some kind of talk about mathematical system, mathematical abstraction, is that obviously we need to build a system, build a physical system to replicate the actual one. Then we have to study that to see, for example, is it stable or not, what are the conditions of poles and zeros, and then we have to forward to the physical system. So talking about the physical system at the very beginning of the point would be a cumbersome, because as you can see, it can be very kind of complex. It's going to be has lots of some kind of problem with that. So at the very beginning of the point, first of all, it would be better to talk about mathematical abstraction, that by using this some kind of method, we can see what is happening between different systems itself. As you can see, we do have, for instance, two series systems that are side by side by each other. We do have feedback loop part and so on and so forth. So at this point, imagine that you are going to hand it the 12 component schematic, and on the other side you have the 4-block diagram of the same system itself. So obviously the one that you choose would be the 4-block diagram one, because the mathematical model is going to be way simpler, and after that you can decide the whole system, predict what would happen on the steady state scenarios or in the transient state scenarios, and then we can decide that whether we can build this model or not. So at the very beginning of the point, we have to start with a couple of definitions. I mean, you already know about that, but it is good to review. Imagine that you have the feedback control loop system, and as you guys know, we call it as a closed loop control system. So for each control system, we do have different parts. The very first part is about the input. Input most of the time is a set point, or is a number that we will like read to our system, reach to that. Then we do have another part, or some kind of, we do have the summing junction, that this guy would be considered as an adder or subtractor based on your feedback. It means that this guy is there in order to find the difference between your feedback and your set point itself, and then it can make a signal, what we call it as an error signal. So this error signal would get injected inside our main guy, going to be some kind of, for instance, at this point is just a multiplier, but again, this is a controller system, it can be anything. Then this GS is going to produce something that we know it as that output, and the whole process is going to be repetitive from one point to another. That we call it as what? That we call it as some kind of back controller. So for an engineering challenge, imagine that you're tracing a signal. A summing junction received some kind of the positive RS from the reference. This is going to RS, and we do have negative CS that we're going to this guy. Why we call it as negative CS? Because it's going to be subtractor, and my feedback obviously is going to be negative. So from the output, what is the exact output of the junction itself? It is very obvious that ES is going to be RS subtracted. Simple. So as I just talked about it, at this point we would like to see what would happen if you do have different systems or combinations combination of systems beside each other. The very two common format would be about the series connections that we call it sometimes as cascades, and we do have it at the parallel connection. So it's not that kind of a challenging thing. Imagine that you do have a system, or actually you have the combination of system that it has controllers G1, G2, and for the final one, or if you would like to find the final combination of the system, or call it as the equation visualizers at this point. So the only thing that you have to do is just multiply by each other. Is that your overall system or overall transfer function would be G1s multiplied by G2s. So this some kind of, at this point, the good thing is that order does not matter for if we are talking about the linear time invariance. That means that if you do have the G1 at first or G2 at first, again, it doesn't matter. You have to just multiply. So cascading of n first order system is going to create what? Create the nth order system. Imagine that you do have a point that the G1 is 10 divided by s plus 5. So as you can see over here, we do have a system that it has a pole as -5, and the G2 would be 3 divided by s plus 2. So what's the transfer function? Poles and DC gain. It is simple. The only thing that you have to do is just multiply these two guys. If you multiply these two, you do have a system like this. 30 divided by s plus 5 multiplied by s plus 2. Obviously, the poles would be -5 and -2, and the DC gain means that what? DC gains meant your s is going to 0 itself, or we know that time is infinite, and since the frequency and time are going to have the indirect relationship, means that your S do that, your DC gain would be 3. Simple as that. And another point, we do have another connection that we call it as a parallel one, and at some point you may hear that feed-forward connection. So at this combination, we do, instead of just having them side by side, you do have it in your parallel. And finally, your final model or your final transfer function is going to be one of them plus another one. So the poles are going to be unions of all of individual block poles. However, you have to be very careful about that. Why? Because at some point, when you combine some kind of fractions together, your poles are not going to have that much of a change at all, because you're just going to multiply them together as the common denominator. But at some points, you're going to make some zero. So the algebra over here can create the new zero cancellation. You have to be very careful. For an example, imagine that you do have your system 2 divided by s plus 3, and another system is 1 plus divided by s plus 1. So if we do have this kind of parallel condition, the only thing you have to do, you have to add them up. Obviously, if you're trying to add them up, you have to find a common denominator, and then your numerator would have some change. It would be impact. So if you find that at the end of the day, you do have a system like this: 3s5 divided by s plus 3 times s plus 1. Unlike the serious condition that we don't have any change in the zeros, at this point you can see that due to the fact that you guys are added together, we do have two zeros. So we do have the poles at -3 and -1, but at this point we do have a new zero that would be there. And as you guys know, considering the zeros is very important, because if you remember, for the last session talked about it, that if you consider the zero, well, your system would have some kind of specific transient response. And another point, if you do consider that, or if you don't consider that, you're going to call it for yourself. So the master equation that we all know, I mean, we saw it so many times, is about the back loop. So as you can see over here, still I do have R as my input, E is going to be my error, and imagine I do have my what? I do have the negative feedback. So if I do have the negative feedback, my main formula, which was the transfer function of the whole system, is equals to GS divided by 1 plus minus GS times HS, is going to be what? Is going to be positive, means that my gain or transfer function's gain is going to reduce. On another hand, if my feedback was positive, this guy would be negative itself. And maybe for some of you are a little bit curious about what would happen. So the only thing you have to know that the C, which is going to be your output, is G, or if you consider as a gain or multiplier or anything it could be, times your E itself. So what was E? E was the subtraction between R and the CH. What is H? H is the feedback gain, and the C is the output itself. So if you use that one, and if you rearrange everything by finding the TS, which is going to be your output divided by input, you still can reach to that one. I will put it on some kind of shoulders because I believe it's simple. So at this point, we do have a very simple example. Imagine my GS is going to be 5 divided by S plus 2. My HS, which most of the time is 1, which is the feedback loop gain, is going to be 1. And we have to find the TS and the DC gain. So obviously, the only thing you have to do, put these values that you have over here instead of these values over here in this equation. And at the end of the day, your TS is going to be something like this: 5 divided by S plus 7. So your DC gain is what? Your DC gain is going to be the time that S is equals to 0, so it'll be something like this. As you can see, the main gain or some kind of open loop gain was 5, but at this point we do have the gain of 0.7. Maybe some of you said that, okay, we are going to lose something, and another point said that, yeah, that's fine, but open loop DC gain actually at that point, at the very first part, was 2.5. By the way, if you consider the GS at the beginning, the open loop DC gain was 2.5. Why? Because we do have what? We had the GS as 5 divided by S plus 2. If you saw, or if you heard that I told you as 5, because I assumed that my gain or GS is going to be 5, it means that it's going to be just a multiplier itself. So at this point I had 2.5, but at the next point you have 0.7. It means that my power is going to reduce, but we are going to have a better speed. Maybe at some point you would say that, okay, how come we do have the better speed? Because if you can see over here, I do have the pole at -2, while at this point I do have the pole at -7. And as you guys remember, if my pole is going to move or shift towards some kind of the negative infinite, or moved from the core itself, it means that my system is going to be faster. While I had the less gain, I do have the faster system itself. So what would happen if I do have the two loop reduction? It means that I do have a system rather than only one closed loop system. It has two, that we call it as an inner loop and we call it as outer loop. So what would happen at this point? Again, the very first thing I have to do, first of all, I have to reduce this part to be only one gain. Then I have to consider the fact fact of this guy to be multiplied by this one, and then I have to consider this as the feedback loop. So all in all, your formula, it would be better to memorize that one, would be what? Would be G1 times G2, which G1 was your outer loop gain for the open loops consideration, and 2 is for the inner loop, divided by 1 plus G2 H2 plus G1 H G1 1. So at this point, we do have a very simple example over here. It means that imagine that your G1 is 2, 2 is this guy, and H1 is going to be 1 and H.5. So you have to find the TS itself. So it is very simple. The only thing you have to do, you have to put everything over here. But remember that this formula is for a time that your feedback loop is going to be what? With a negative back, which most of the time is negative. So if you put all of these answers together, your final value is going to be what? 6 divided by S plus 8.5, and your DC gain 0.7. Simple as that. But at this part of this, some kind of example, or some kind of the presentation itself, we would like to consider the scenario. The scenario that at some points, maybe you would like to change your point. This part, we call it as a pickoff. Maybe you would like to move it from one place to another. So obviously, at the end of the day, the signal that you see from the outside shouldn't see any kind of changes, despite of the fact that you are getting your output from one place or another. So imagine that I do have a system. My system is like this. The input, and after that, this input just go through the G, and after that I do have C as my outer signal. So C is equals to R times G. But imagine at another point I don't like to get my signal out of that place. I would like to get my signal over here, or I would like to move my pickoff to the left. So if I just consider that and don't change anything, at the end of the day, my outer signal, which is going to be just R, as you can see, there's a huge difference between R and GR. So it means that I already lost something. In order to compensate that, we have to put another gain between my output and the new place itself. And that gain should be exactly as the same as the normal gain that we used to have. So my system would be like this. So what would happen if I do the Y split? It means that what would happen if I move the pickoff to the right? At the first point, I had my system at this place, but at another point, I have my system or the outer point that's at this place. So at the first part, my C was R. It's not going to see the G at all. But at another point, this guy is going to see the whole G, just like the previous side. How I can make sure that the outer signal is going to be the same as this part? The only thing I have to do, I have to add the inverse gain is going to cancel out the main gain, which was the G itself, because as you know, at this point, I'm going to see the RG instead of just R itself. And at the end of the day, I do have the R itself. So about the summing junction, it's not very important, because at the end of the day, we know that if our system is going to be linear, it doesn't matter if this guy comes first or this guy comes second. At all of them, the only thing you have to do is just a multiplication. I just added an example over here for you. Obviously, you can just read it. It's very, very simple. Another thing that we have to see is actually the combination of all of them. So what would happen if I do have some kind of inner loop? An inner loop is like this, and I do have another parallel scenario like that one. Then I do have another gain like this, which is going to be in series, and then I do have I do have a feedback loop. Let's solve this. So imagine our system is like this. So obviously, if you would like to do the reduction in blocks, you have to start from the inner part and then move to the outer part. So at this point, I would like to know what is the combination of all of these blocks together. What's my main TS over here? What would happen to my main TS? So as I just mentioned, we have to start from the inner side. As you can see, for my inner side, I do have something like, and my H2, I believe, was 1, right? Yeah. So my H2 is 1. So the only thing that I have to do, as you guys remember, I do have this block, and after that, I do have the negative, some kind of feedback block. So for instance, I can call it as T1S, or I can, whatever, it doesn't matter. You can name it. So T1S is going to be, better to use another one. T1S is going to be G2 divided by 1 plus G2H. Is that okay? It means that G2 divided by 1 plus G2H2. So this is going to be T1S. It means that I can get rid of that, and I can just add T1S itself. So at this point, I do have one block, T1S, and I do have another block that is going to be in parallel with that one as S plus 1. As you guys know, the only thing that we have to do in order to combine these two guys, we just add them together because they are parallel, so nothing would happen, right? So T1S plus GFF is going to be 1S divided by 1 plus S plus 1 plus S itself. So as you guys know, the only thing we have to do is just find the common denominator, which is going to be 1 plus S. I can write it down. Is going to be S plus 1 plus S to the power 2, S2 plus 2S plus 1. So at the end of the day, I do have S2 plus 3S plus 1 divided by S plus 1. So this guy would be the combination of T1S and what? and my s plus 1. So at this point, everything is okay. Right now, I do have some kind of signal that we are going to take care of. Then we do have another signal that is going to be in series with that. So as you all know, the only thing you have to do is just multiply it with that specific signal. So multiply it by k, or G1 is going to give you what? K times S2 plus 3S plus 1 divided by S plus 1. As simple as that. Am I done? Obviously not. If I consider that there's another H over here, which is going to be my negative feedback loop, my final TS would be what? My final TS would be K times S2 plus 3S plus 1 divided by S divided by 1 plus K, which is going to be this guy again, and multiplication by this guy, and the only thing I have to do is just multiply everything by another S. But as you guys know, since this S is going to be in the numerator and this S was in the denominator, they're going to cancel out each other. So it would be 1 plus K times S2 plus 3S plus 1. So obviously you can some kind of simplify that, and it's going to be very simple. So as you just saw, if you know the fundamental part, you can do anything that you want. It doesn't matter how some kind of complicated your blocks combination would be. So let's see a real world action. Let's see, for instance, we do have the antenna azimuth control, and this physical system would be like this. We do have the input, we do have the potentiometer, then we do have the controller on the side, we have the electric motor, and finally we do have the satellite antenna. So as I just told you, we are going to use the mathematical combination or mathematical some kind of model in going to replicate whatever happening in our physical world. So let's see what would happen. A potentiometer is just going to be like the gain. It's going to be a multiplier. So okay, then we do have the controller. Imagine our controller is going this, and then finally we do have what? We do have our electric, some kind of motor is not going to do anything. Our some kind of the controls is going to be 1, and finally our feedback is 1 as well. So at this point, we are going to test the proportional controller over here. Imagine that the KP is going to 10 and is going to, does it pass this going to speak or not? So if you some kind of do the combination, and if you have everything that you need over here, your T or transfer function is going to be 100 by imagine that the KP or the proportional controller at this point, because we do have for instance at this point we do have the potentiometer, or we can have the proportional controller. It means that these two guys either can be combined and be to one controller, or you can just have this guy as a potentiometer. It does. So at this point my transfer function is going to be 100 divided by S to the power 2 plus 5S plus 100. So if you guys know, based on the formula that we had, because this is going to be the second order system, the 100 is going to be omega n to the power 2. Omega n was about our frequency response, and then our zeta or damping is going to be 0.25. By having these two and put it inside the specific formula that we saw in the last part, we see that what? We see that our underdamping is going to be, we do have the underdamped system is going to be 45% overshoot. How we can compare this number is going to be valid or not? We have to see the system specs, because the system specs told us that our some kind of bandwidth is going to be a little more than 2 Hz, and our target tracking is going to be positive negative 0.5 Hz. So finally, we have to see that it's going to be this, all of these numbers that we found are going to be okay or not. And we can see the specs fails, because what? A more advanced controller is required at this. You compare these two systems together, you see that this is not going to be the thing that we like. We need to make our system more advanced. At this point, our controller is very simple. We also have to consider a couple of important troubleshooting section, or we have to see a couple of failures or faults that be very careful about that. The very first thing is about the wrong sign in the feedback itself. If you guys remember when I told you about the closed loop feedback controller, I told you that if your feedback is negative in your final formula related to transfer function, it would be this, for example, divided by 1 plus times a. And if you forget about that, and instead why you see a negative, you see that okay, it is good, that is good. It means that I can make this one as negative, everything would be collapse. So one thing that maybe would be considered as a rules of thumb is that if you do have the positive feedback, your gain is going to reduce. At what point your gain is going to reduce? If you do have the bigger denominator, and the bigger denominator means positive. The second error would be about the outer loop before inner one, which is some kind of the common issue. It means that when you are trying to simplify all of those, some kind of the inner loop and outer loop combination, if you guys remember about that, and the formula itself is that at some point you use some kind of mix and match the gains and any kind of information related to an outer, and you just put it into vice versa and some kind of in the missed place. So at this point, your answer is going to be what? You're going to answer problematic. And dropping the pickoff point, very, very, very important. You guys know if we move to the left side, and for the pickoff point means that move to the left side of our some kind of controller, whatever the gainer, whatever the value was that one, you still have to consider what? You still have to consider the exact same gainer while you have your pickoff. On the other hand, move it to another side, you have to find the reverse of that. This is very important, and deleting blocks, which is not kind of a common issue, but you really have have to be careful about. And the real world architecture is about the closed control type 1. What does that mean? Imagine that you do have a system is like this. I do have, this is for the for the actual closed loop control for the vehicle dynamics. It means that this is the actual controller and actual system. I do have the PI controller, so KP is going to be for proportional, and I controller is going to be for integrative. And then I do have what? I do have the vehicle dynamic based on the mass and based on the drag itself. And then I do have what? I do have a sensor as considered as what? As a feedback control. So why, by the way, we call it as some kind of type 1 system? Because if you find your TS or if you find your transfer function at the end of the day, you're going to have what? You're going to have S as integrative in your denominator and is going to be to the power of 1. That's what we call it as type 1 itself. So imagine that we do have a system like that one, and I do have some numbers like this. This is my KP, this KI, and my target, which is going to be my RS, is going to be 30 meters per second. So at this point, I'm going to see that what is my some kind of steady state error. So because we do have the PI controller is going to add KI over S, it introduces the poles at the origin itself. It means that this type of this kind of specific controller would be considered as a type 1 system. Steady state error to step input is mathematical 0, and it means that the speed is going to be exactly at 30 meters per second. Why we're saying that? Because as you guys see over here, I do have the system, and after that my system is going to have a very massive block on the top, and after that it's going to have what? Is going to only have one feedback loop. If you find that your some kind of formula itself, at the end of the day, we have to find what? We have to find the error at the steady state. And for finding the error at the steady state, we do have this simple formula. We just talked about it before. The ES is going to be the limit of S times your value itself. But if you find this calculation, at the end of the day, you will find a value of 30 divided by 1 plus 500S or something. So if you have this value, or have 30 and divided by specific value in the genome. So if you put your S as 0, and if you consider all of these some kind of calculation, you would see that your denominator would be infinite. It means that you are going to face the issue, not an issue actually, it's a fact. You're going to see an issue that in the denominator, you're going to have the fraction, and the fraction itself, its denominator is 0. So obviously any number, for instance, 5 divided 0 is going to be infinite. So what would happen at this point? The 30, which is the infinite number divided by infinite, is going to be something around 0. So by something around 0 means that at the end of the day, you don't have any error, or steady state is so close to 0. And at the end of the day, you can consider the fact that, okay, some kind of our controller is going to work fine itself. So at the end of the day, I do have the tool selection metrics, and based on some kind of your usage, you can see that which one of those values or which one of those methods that you have to consider for your work itself. As you guys can see over here, the black diagram has the intuitive visualization. We have the systematic reduction we can use, but it cannot handle some kind of the nested loop. It means that if your loops are going to be a little bit higher in numbers, calculation would be very complicated. So it's not very proper method for that time. And algorithmic one-step solving, which is not going to be proper for that. Another thing that we do have the signal, some kind of flow graphs, and we do have the state space. So this guy, we didn't talk about that one. In future lessons, we are going to see that, and state space, obviously we talked about that. So the state space is not going to have the very intuitive visualization, because as you guys know, we do have multiple output. While it's going to be good for the system reduction, it can handle some kind of the system when you have 5 nested loops. But as you guys remember, if your system is getting a little bit higher numbers, like more than 20, again, it's not the free feasible part, and this guy can do the one-step solving itself. So the key insight over here is that block diagrams are exceptionally intuitive, but breaking down mathematically at a high topological complexity is that when your system is getting some kind of complicated, they are not going very feasible itself. So as you guys saw right now, we do have another part and last part, which is last slide, which is going to be about the engineering decision. It means that, okay, at what point should I use what method? Imagine that you do have a system. The very first question that you have to ask is that, do I need to track the internal system states? If I need to use the internal system state, the very important thing that I can use is state space, because as you guys know, the state space is going to be very comprehensive method if you want to understand actually what is happening inside your system. If my answer is no, at this point I have to see that how many loops actually exist in the system itself. If I do have only 3 loops, okay, that's fine. The block diagram is going to be fast. But if I do have more than that, means that I have to use other methods like the Mason's one, SFG, that we are going to talk about it in the next chapter itself. And this is going very simple summary that what we covered today obviously was way more. So as you guys just saw today, we talked about the very important way of mathematics solve the some kind of the system, or at least the mathematical configuration of that, and using just a block diagram. What would happen to have the combination of block diagrams series in parallel? What would happen to have the complex scenarios, and what are kind of issues that faced before, and you really have to be careful. For the next chapter, we are going to dive a little more inside detail and try to talk about other functions, because as we just saw right now, this block diagram have limitations. Why it's good for some kind of, what can I say, simple, I can say less complicated models, very challenging, very complicated model, because you are dealing with so much mathematical complexity. So that was this today chapter. Have whatever